Yeah, hi. So I'm going to be presenting something about the spatial patterns of tech, particularly when you have large events, which is for space weather applications, I guess. And here you have a bunch of the people that we're working with, particularly people from the Servicio Sismológico programa. Thank you. Well, okay. Yeah, sure. And the Departamento de Física, which is from where I'm from. I like this quote, which is, I think, is represent me quite well. It is nice to know the computer, understand the problem, but I would like to understand it too. Okay, so always keep that in mind in this presentation. So what I'm going to be talking to you is about total electron content. I'm going to be using it to monitor complex solar magnetospheric ionospheric dynamic coupling, particularly. I'm going to show you we have developed an open source code. You can actually install it in a standard way you install things in Python that you can use for this. And particularly, I'm going to show you some high resolution patterns during a very large perturbation for particularly one very big storm that we have been doing. This open source code, by the way, has been validated. So I'm going to be presenting a little about how we're interested particularly when you have very large perturbations to the ionosphere. And we are working in the process of constructing a model to try to understand the physics of the whole magnetosphere and atmospheric interaction. Here is the validation. As I said, we have developed this Ionotech open source code that you can install and use if you want. This has been validated in this I have a pointer. In this paper initially, which Manuel was presenting before, or partially presenting before. This has been compared with all these codes, Semala, Ciraolo, etc. And you see that it works quite well. This was done, for example, for the eclipse of 2019. And you can construct it for as many as you want. We have done it. That's, of course, that was for quiet conditions. This has been done lately on a mild storm using data taken from the very high resolution data available in Chile by the Centro Sismológico Nacional, which has a lot of antennas all over Chile. And here we compare with all the standard models, Ciraolo, Semala, etc. And we are doing quite well with them. And it was very important to do it for a milestone to try to see whether these models are able to handle the system as you increase and you go over stronger and stronger systems. This has been sort of validated with ionozones. Here you have, for example, this is the ionozones. This is a paper that was just submitted. Ionozone with actually the measurements of tech or the estimations of tech, and is doing very well, except when the system is kind of active and you have a lot of noise, of course. These are from the 3 models that I told you, and also IonTech is here if you want. So, and here you have for this reasonably mild storm how Ionotech is looking at the ionosphere at different times. So this is working quite well. And one of the things that we are trying to do in this process of constructing models for very active times, we were trying to do particularly this is a mild storm, so it's not extremely active, but reasonably active. Of course, you have to start walking and then running. You can see what are the cross correlation between, for example, different magnetospheric indices, KP, with tech, and you see that you see this variation in space. And this is, for example, with DST. Of course, it will be blue because there's an inverse correlation. And other things like F10.7, etc. And it is important to do this work slowly because if you want to construct a predictive model based on machine learning or whatever you want, you want to know exactly what are the parameters that you want to use to try to construct these models. We have a lot of experience in doing this, for example, for space weather applications. And if you don't do that, you start confusing the models. Here you have, for example, AU and AL. AU and ALs are electrojet indexes. And you see that the contribution is not that amazing. There's a little correlation, but not that much. And, oops, sorry. And you can also check with different X-rays levels, soft and hard, or medium, high X-rays. And you can see that there's a little correlation. So you can do that, use that information, of course. And then we say, okay, let's go for a big storm. Here you have the Mother's Day geomagnetic storm 2024. The DST went to 406, which is quite high. And we're going to combine the high resolution spatial data of the GNSS data from the Centro Sismológico Nacional, but also we're going to combine it with cellular phone data that is freely available from this paper. 5 minutes? Sure. 5 minutes? Is that what you? And here you have, for example, the comparison. This is before, this is DST up here. And this is for a quiet time. This is the first column. This is combining IGS and the Centro Sismológico Nacional. And here we have the high resolution data that we are using. And the one below is when you just put the cellular phones also, which are freely available. Then when the shock hits the magnetosphere, we start, of course, looking at the perturbations. You have a lot of data from the cellular phones. Those are very amazing. And then we start looking at the very active time, and you see this is the data from the Servicio Sismológico. You see a very active tech on top of Chile. And you see when you include, of course, these cellular phones, you see that they are looking quite well. Then you can go a little later, exactly at the maximum. At the peak of the storm is a minimum, of course, in DST. And you can see, again, the very high resolution data and including the cellular phone. And then, also you do it in the recovery phase if you want to see how things are. And this is very nice because it provides a lot of data even when the cellular phone is not available at certain times. And you can try to see what are the drivers of this, for example, it's quite interesting physically that, for example, when the DST was quite low, minus 351 nanoteslas, you have a very active tech, but then a little later, over Chile, a little later, 4 hours later, more or less, you actually have a very inactive tech response close to over Chile. So it's interesting to start looking at what are the data, what are the parameters that are acting, what the parameters are probably producing the response that we're observing. So you can correlate, for example, with the KP index, DST, the terminator or the auroral boundary, or even tech in other places like Europe. And it's quite interesting that the time delays are very interesting and very non-trivial when you want to do very large events. These are, for example, solar protons events that are quite interesting. And I think that if you want to do this for very high events, probably you have to start combining these with magnetic fluctuations because they provide quite a lot of information also. This is something we just submitted that you can do magnetospheric magnetic field fluctuation response, the spatial patterns in the northern hemisphere where there's a lot of magnetometers. Sadly, in the southern hemisphere, there's almost none, but we're working on changing that. And I think, just to finish, I think for very large events, if you're trying to study use tech to monitor space weather large events is quite useful. And we're working in trying to understand how this can help us understand a little about the sun magnetosphere and ionospheric coupling. Okay. And I think they can complement, especially when you have very high spatial resolution, it can complement a lot um, uh, things like for example, the cellular phones that are available. And I recommend you using IonTech. It's very stable. We have checked that it's working quite well compared to the other one, and it's also open source. So I invite everybody who want to change and play with it, that is freely available. This is the people who support the work, of course, and from the people I get the data. So thank you very much.